Okay, let's now talk about renal clearance. Okay, we talked about clearance in general. We talked about metabolic clearance, in which we had emphasis on hepatic clearance, and we talked a little bit about renal clearance and the processes that we have and renal system and the nephrons and the differences kinetic wise in each one of them. If you remember before when we had rate of elimination, okay, over concentration at certain time, this we called it total clearance, right? And I mentioned if we want to have metabolic clearance, this would be equal to rate of metabolism over concentration at certain time. If we want to have it as hepatic, would be rate of hepatic metabolism over concentration. Or if we want to have it as renal, that would be rate of excretion over concentration at certain time, at certain time. Okay, we had this already before. So if we go back here, the renal clearance or R or just excretion, sometimes it would be equal excretion rate over plasma concentration at certain time, which is the change in the amount excreted in the urine per unit of time or over time over the concentration measured in the plasma. But again, under healthy condition, for any drug that is cleared in the kidney, the rate of, let's consider this is organ, the rate of N should be rate of out if we are talking about healthy organ or healthy physiology of the kidneys. So going through the kidneys via the process that we have, whatever the process, should be equal to the rate excreted in the urine. So we can take it another way that the excretion rate that we already know it in here, okay, could be also um, presented or calculated or estimated knowing the rate of the urine flow and the concentration of the drug in the unit. So this is another concept that we can talk about, that other than glomerular filtration, tubular secretion, or reabsorption, we can determine it from some information from the urine. Okay, again, we have rate of, let's go back, we have rate of excretion over concentration in the plasma. Okay, just let's go back to whatever we know about the rate of excretion in the kidney. We have glomerular filtration, we have tubular secretion, and we have tubular reabsorption. Again, this would increase the excretion or the urine volume. This would increase it, this would decrease it, right? Because it will go back to the nephron or the tubules. Okay, so if we are talking about rate of excretion, it should be the sum of all the processes that are involved: filtration rate, secretion rate, minus reabsorption rate, which means if we go back here, the renal clearance would be equal concentration um, in the plasma, okay, and this would be equal glomerular filtration rate plus tubular secretion rate minus tubular reabsorption rate, okay, whatever is involved. And again, this definition of the clearance would be also called physiological definition or physiological model of the clearance in the renal, because we are taking into consideration one organ a clearance, specific clearance, and we are taking into consideration different physiological processes that is involved. Okay, There is something that we can measure that is called a clearance ratio. And again, this is as a qualitative way to determine whatever is happening. Again, qualitative initial estimation of whatever is happening in the excretion of the drug. And the clearance ratio would be equal to the clearance of the drug over the clearance of aniline. Let's just go back to whatever this was. The aniline was the material that we use to measure the kidney function, in which the drug or this material is fully filtered through glomerular filtration, no reabsorption, no excretion. So this is the total that we can have as glomerular filtration, right? So we can use this ratio to determine whatever is happening to the drug again as an estimation to start your research or your experiments. If the clearance ratio is equal to 1, it means that the drug is filtered only. If it's less than 1, it means that there's something that is taken out of the filtration or the filtered volume or the ultrafiltrate. So we have, in addition to the filtration, partial absorption. If it's more than 1, it means that some of the secretion is happening to the drug. Okay? So let's go here, which is very important, is an example of profiles or sketches that we can have for the excretion of the drug. Let's see here, you have excretion rate versus plasma concentration. Let's draw, first of all, each one of them alone. So we have concentration, rate of excretion versus concentration in the plasma. Okay, let's consider that I have glomerular filtration only. Okay, we said that the glomerular filtration is what passive processes or linear processes, or kinetically they are following first order kinetic. So rate of the process versus concentration would give me linear profile. So this is glomerular filtration. Okay, if we are talking about let's say tubular secretion, okay, which is totally what active a process. Okay, so if I want to which is nonlinear, which is very important, and this we had it as linear, right? So if I want to draw nonlinear process, it would be something like that, in which we call it nonlinear or capacity limited, or a saturable profile, in which we have the saturation here because all of your enzymes or transporters or carriers are fully occupied. Okay, so and the let's say the tubular reabsorption, we mentioned that it could be linear, it could be, which is the majority of the processes, it could be active as passive or active. If it was, let's use different color for each one of them. If it was, or if it's passive, then the profile would be, again, it may not be the same as this, but I will use the same as this profile. Okay, so it would show a linear profile. So this is for passive tubular reabsorption. Okay, if it's let's say active, okay, so if tubular reabsorption is active, it would have similar profile to this. So this could be also for active or nonlinear tubular reabsorption. And again, I'm using the same profile, but it may not show similar profile. It may be like this. And here, It may be like this. Doesn't matter, it should be at least linear. Okay, which the take-home message of this profile are these sketches that if we are talking about glomerular filtration, tubular secretion, tubular reabsorption, the profile should be rate versus, let's just, glomerular filtration rate, concentration. By the way, just a correction for that, I just noted that it's the rate of the process that we are talking about. This is very important, and we will talk about total now. Okay, so this could be glomerular filtration rate, tubular secretion rate, or tubular reabsorption rate. So I'm talking about each separate profile. Okay, so for glomerular filtration versus concentration should be like this. If it's linear here, again, tubular reabsorption rate versus concentration would be linear. If it's nonlinear or active, it would be saturable. If we are talking about tubular reabsorption as tubular secretion rate versus concentration, it would be for sure active, okay, which is nonlinear. So this is the take-home message. So in here, one example that we have glomerular filtration and we have tubular secretion, we have no tubular reabsorption. This is an example. So the filtration only if we are talking about excretion, if we are talking about involvement of filtration only, okay, let's use brighter color. Filtration only, it would be linear. If we are talking about secretion, tubular secretion, which is active, it would be nonlinear, saturable. Okay, what if we have a total according to the example that we have, which means that we have glomerular filtration and we have tubular secretion, which is linear and nonlinear together. Okay, what we will have, you will have something at low concentration at certain until certain concentration. The profile is showing um, similar behavior of the nonlinear. Then until certain concentration, the drug is behaving similar to what? Similar to the linear profile. What is happening here? Okay, this is the total again. If we have glomerular filtration and tubular secretion, whatever is happening here is that we are having at low concentration, the dominant process here is the active process because the transporters or carriers that you are having are still not saturated. So the active process is still dominant until we reach a point, which is actually from here to here, before we reach the saturation or the plateau of the active profile, the all of the sites of the transporters or the enzymes or whatsoever involved, they are occupied, so the active process is not effective anymore. Then at higher concentration, the dominant process would be the first order process or the filtration. Okay, so this is what is happening here. Okay, okay, let's see here. We have a graphical way to determine the clearances of certain drug, in which in here we are having rate of drug excretion as rate of excretion, again as amount excreted in the urine per time, okay, versus concentration. Again, we are having rate versus concentration of the excretion here. So if we are having the excretion rate, it would be equal the renal clearance multiplied to the concentration, which is the same as I mentioned here. Renal clearance would be equal rate of excretion over the concentration in the plasma. Okay, so this is drug A and drug B. Graphically, can you determine if the clearance of A is more or less than the clearance of B? Yes, because the slope of this profile, as we mentioned before in the IV bolus chapter, would be equal renal clearance of A, and the slope of this profile would be the renal clearance of B, which means that if, or as it's shown here, because this is the A profile, okay, because the A profile showing rate of excretion versus concentration is steeper. This line is steeper than this line, which is showing the excretion rate of B, then the renal clearance of A would be larger, okay, because it's steeper as line, okay, which means that the renal clearance of A is larger than renal clearance of B, or the renal clearance of drug B is smaller in value. Okay? Okay. If we were able, let's me write it step by step so you can follow me. We have before total clearance equal dose over area, total area under the curve. This is again, just be careful. This is total clearance and this is total area under the curve. Okay, so if we want to have it in terms of renal clearance over total area under the curve, we need to have cumulative amount excreted in the urine that is total. Why? Because I'm using total area under the curve here. And again, because I'm using renal here, it should be excreted amount cumulative excreted in the urine total. Okay? Again, we were determining this from CB versus time. If we are talking about IV bolus, it would be area under this profile. If you remember the profile of this, is this, right? Amount excreted cumulative in the urine, okay, versus time. And again, for this profile, nothing is changing. It's still from CB versus time. But we mentioned that we have some problem in the amount excreted cumulative from 0 to infinity. If you remember, what was that? That we can't experimentally reach infinity time. So we were using 5 or 7 half-lives experimentally because we can't reach to the infinity time. So we are having either more than 95 of the drug excreted or more than 99 of the drug is excreted. So accordingly, if we will use, let's say, renal clearance, but we want to estimate it from amount excreted in the urine cumulative from, let's say, 0 to certain time. Let's say I want it until certain time in which I can reach 5 to 7 half-lives, 5 or 7 half-lives. This would change the area under the curve I need to use, which is 0 to t. I can also have it from excreted in the urine from certain time to another time over area under the curve. So we need to correct for that from T1 to T2, which means like I'm taking certain time from this time to this time, I need the cumulative amount in between those two times. And again, whatever that you use, this is experimentally not feasible, but you can math-wise do it. Whatever the way that you are estimating the clearance, you need to know that it should be similar to each other, because as estimation should be almost the same number, because we mentioned that under linear kinetic, the clearance is what? Constant. And this give us or transfer us to this sketch. If I want to draw drug excreted in the urine, which is drug excreted in the urine versus from zero cumulative from certain time to another time. I'm using it from zero to certain time versus zero area under the curve from zero to certain time, which is similar to this one. If I'm drawing this versus this, I should have linear profile with a slope that is equal to what? Renal clearance. The same thing if the amount was from time 1 to time 2 and area under the curve from time 1 to time 2 should be linear and the slope should be equal renal clearance. And this two sketches, in addition to this sketch of two drugs, we have one condition. Okay, so again, and we had either rate of excretion, whatever the excretion, versus um, concentration in the plasma. We had this or this or this profile whatsoever, A, B, C, for different drugs, or you have amount excreted in the urine, cumulative whatsoever from zero to certain time versus area under the curve. Let's use this from zero to certain time. So this is zero to certain time, and we had this. Those profile would give me renal clearance of the drugs that are graphed or are that we are talking about under one condition, right? What is this condition? We just mentioned this couple of times. So just think about it. What would be the condition of having the slope equals the renal clearance? Okay, and